Hello seniors, today we're going to see electronic assignment 14, which is about the derivative and graphing. As we have seen in previous classes, we started analyzing the applications that the whole concept of derivatives has on real life applications, right? So now we're gonna get more into the graphical interpretation of derivatives, and we're going to be analyzing how to interpret the first derivative, the second derivative, and how they are useful in order to find important pieces of information of specific graphs. Okay, so as you can see, we have lots of objectives for this class. This would be a class that would have maybe 2 or 3 tutorial videos because it's kind of long, but it's pretty interesting, and if you understand this clearly, then problems won't be very difficult. So the derivative and graphing. Objectives: interpret derivative as gradient function and as a rate of change. That's something you already know. Define and apply the second derivative of a function. You already know how to find the second derivative, but we're going to see how it applies to graph analysis. Calculate higher derivatives when required. You know that already. Find local maximum minimum points. We're going to see that very important application of derivatives. Verify if a turning point corresponds to a maximum or a minimum. You're also going to be seeing that. Determine points of inflection with zero and non-zero gradients. You're going to see what inflection points are. And finally, understand graphical behavior of functions, including the relationship between the graph of f prime, and the second derivative of f. Okay, so it says, one of the most powerful uses of the derivative is to analyze the graph of functions. In this section, you will see how to connect f prime with the second derivative to the graph of f. A function is increasing on an interval if an increase in x results in an increase in y. A function is decreasing on an interval if an increase in x results in a decrease in y. Okay, so that's something logical, right? An increasing function will look something like this, and while a decreasing function will look something like this. It'll go down as x increases. Okay? Then it says, when a function is decreasing, the tangent lines to the curve have a negative slope. And you can see that right here, right? In the first part of this function, it is decreasing, right? And if we trace tangent lines, as you can see, the blue lines there, the tangent lines throughout all those sections have negative slopes, while in this part where the graph is increasing, the tangent lines have positive slopes. They are increasing, right? So when a function is increasing, the tangent lines to the curve have positive slope. It follows that. So here's the rule. Remember that the derivative of a function gives us the value of the slope of the tangent line at a given point. So from that concept, we can determine these rules. It says, if the first derivative, or if the derivative of the function is positive, that is greater than 0, then the function is increasing in that interval from a to b, okay? And if the derivative of the function is negative, or less than 0, then we can conclude that the function is decreasing on the interval considered, right? So that's the basic thing from this first part that we're going to see today. So it says, example 22, use the derivative of f to find the intervals on which f is increasing or decreasing. So we're going to be analyzing these 3 functions. We're going to determine the intervals in which each of these is increasing or decreasing by applying the first derivative in this case. Okay, so here are some concepts. It says a stationary point is a point where the first derivative is 0. So a stationary point can be a maximum or a minimum point, or maybe an inflection point, which we're going to see what they are about. And then it says a critical number of f is a point where the first derivative is 0, or also where the first derivative is undefined. Okay, so let's see the first example for part A. If we want to find the intervals on which the function is increasing or decreasing, the first thing we need to do is to find the derivative of the function, okay? So let me copy the function first. It's f of x equals 2x cubed minus 3x squared minus 12x. So the first thing I'm going to do to see when the function is increasing or decreasing is to find the derivative, right? So this is 6x squared minus 6x minus 12. Okay? Obviously, if you have your calculators with you and you are allowed to use your calculator, all of this process becomes much simpler, right? Because you can just graph this function and see when the function is increasing or decreasing. But if it's a paper one where you are not allowed to use your calculators, you should apply this concept in order to determine when the function is increasing or decreasing. Okay, once we find the derivative, we're going to set the derivative to 0, because we know that when the derivative is 0, we're going to find the stationary points, which are the points where the function has a minimum or a maximum. For example, in this particular graph here, we're going to find this point over here where the derivative is 0, right? Because the slope of the tangent is 0. It's a horizontal line. So with that information, I will find like the limit where the function changes from being, in this case, decreasing to later on being increasing, right? That's why it is important to find those stationary points first. So by setting the first derivative to 0, I'm going to find those stationary points. So I'm going to set this to 0, and here I'm going to take a common factor of 6. We're going to get x squared minus x minus 2. The 6 gets eliminated because 0 divided by 6 is still 0. So this is 0 equals, and here I can apply multiply add, right? A pair of values that multiply would give me -2 and added would give me -1. So we have -2 and +1, right? So x equals, we write first -1 because it's smaller. X equals -1 and x equals 2 in this case are my critical numbers, okay? What are critical numbers? Points where the first derivative is 0, okay? Or undefined. In this case, it's when the first derivative is 0, so these are my critical numbers. Critical numbers. Once I have my critical numbers, I can make a number line in order to see the intervals for when the function is increasing or decreasing. So if I do a number line, something like this, I'm going to mark the critical points. For example, -1 over here, and let's say 2 is over here. Here, okay? So I know that for those 2 points, the derivative is 0, right? So what I'm going to do is I'm going to analyze what happens before -1, between -1 and 2, and then after 2, in order to see if the function is increasing or decreasing between those critical numbers, okay? So what I'm going to be analyzing basically is the sign of f prime of x, of the first derivatives, the first derivative, okay? So what I'm going to do is I'm going to pick a number, let's say, for example, -2, and I'm going to plug in this value into the first derivative in order to see what sign I get when evaluating the first derivative for that value. So I'm going to calculate f prime of -2. I'm going to replace the values. This is 6 times -2 squared minus 6 times -2 minus 12. Okay, remember I'm replacing this value inside this function over here, which is the first derivative. So this, if you calculate this, let's try not using calculators because the idea is to do all of this without a calculator. This is -12. -12. So this has a negative sign. We only care about the sign. We don't care much about the value because the sign is what is telling us if the function is increasing or decreasing. Remember, if the first derivative is a negative number, then the function is decreasing in that interval. Okay, so with this information, with this negative sign over here, we can already conclude that the function is wait, I made a mistake here. This is not -12. This is actually +24. Sorry, this is 24. 12, yes, 24. So this is a positive number, sorry. So since it is a positive number, we conclude that the function is increasing for before we get to -1, which is a critical number, okay? And if I do the same thing for a value in between, let's say a value in between -1 and 2 could be, for example, 0. If I calculate f prime of 0, sorry, we're going to do the same thing, right? 6 times 0 squared minus 6 times 0 minus 12. And this would give us a -12. So yes, in this case, we have a negative sign, right? -12. So between -1 and 2, the function is decreasing, right? Because the sign of the first derivative is negative, right? That means the function is decreasing. And if I want, I can calculate. I already know that this should be positive because 2 is at 2 the slope is 0, and that causes a change in direction. But in case I'm not very sure about that, I can pick a value here, let's say for example 3, and I can calculate f prime of 3. And this would be 6 times 3 squared minus 6 times 3 minus 12. And if you calculate this would be, give me a second, 6 times 9 minus 6 times 3 minus 12. This is positive 24. So as you can see, this has a positive sign. So we conclude that the function is increasing after the critical number x equals 2. So finally, with this analysis, we may conclude that from negative infinity to -1, without including -1 because the slope is 0 there, the function is increasing, right? The function is increasing. Then from -1 up to 2, the function is decreasing according to our analysis. And finally, from 2 to infinity, the function again is increasing. Okay, so that's the first exercise, and that's all we need to do in these exercises. We found the intervals in which this first function is increasing or decreasing. So we're going to do exactly the same process for B and C. You see that they are a bit different because the functions get a little bit more complex, but the concept itself is the same. Let's see. Part B. I'm going to copy the function f of x is equal to x squared minus 4 over x squared minus 1. X squared minus 1. Okay? So if I want to find the intervals where the function is increasing or decreasing, the first thing I need to do is find the derivative of the function. Okay? So I need to calculate f prime of x. In this case, I would have to apply quotient rule, right? Because I have a quotient between two functions. So if I apply quotient rule, remember it's the denominator. I'm going to do this directly, assuming that you already know how to differentiate. The denominator without finding the derivative times the derivative of the numerator, which is 2x in this case, minus u, which is the original numerator, times the derivative of the denominator, which also is 2x. And this is all being divided by the denominator squared. So x squared minus 1, and this is all squared. Okay? I need to work on with this in order to get a more something that is more elegant, right? So I see I have a common factor of 2x, so I'm going to take 2x as a common factor, and inside we're going to get x squared minus 1 minus x squared plus 4. And this is all being divided by x squared minus 1 squared. So I see that, for example, x squared eliminates with x squared, and I get a 3 here inside the parentheses. So 3 times 2x, that's 6x divided by x squared minus 1 squared. And this would be the first derivative of this function. Okay, so once I have found the expression of the first derivative, the following process is to set the first derivative to 0 in order to find the critical point, the critical numbers, right? So we set this to 0. 0 is equal to 6x over x squared minus 1 squared. Okay, so from this analysis, I get that one value of x should be x equals 0, right? If I set this to 0, we're going to get that 0 is equal to 6x. So one possible value of x that makes all of this 0 is the value x equals 0. But I should also consider what's happening in the denominator. I know for sure that x cannot be 1 or negative 1, because if it was 1 or negative 1, then by making 1 squared minus 1, I will get 0. And remember that any number divided by 0 is undefined, okay? So from that analysis, if I set the denominator to 0, I will get that x squared is equal to 1. So x equals plus or minus, if I do a square root, it's plus or minus 1, right? So for let me do it this way, I'm going to write it down here. For x equals positive 1 and x equals negative 1, we get the function is undefined, right? The function is undefined. Function is undefined. So these three values, let me underline this, x equals 0, x equals 1, and x equals negative 1 are my critical numbers, okay? So I'm going to write this as like this. These are my critical numbers. Because remember, critical numbers are not only the values of x for which the first derivative is 0, it's also the values of x which make the function undefined. In this case, we have two values of x that make this function undefined, positive 1 and negative 1. Okay, so now that I have identified my critical numbers, I need to make again my number line. I'm going to make the number line right here. And we're going to analyze the signs, okay? I'm going to put the critical numbers. Negative 1 over here, 0 maybe here, and 1 can be here. I'm going to extend this a little bit. There you go. So once again, we're going to analyze the signs of f prime of x, of the first derivative. So what I'm going to do is I'm going to pick a value which is less than negative 1, for example, negative 2, and I'm going to analyze that. F prime of negative 2 is equal to 6 times negative 2 over, remember I'm using this one, over a negative 2 squared minus 1 squared. This gives me as a result a negative 12 over 9. So as I told you, we don't care much about the value, we care about the sign. So we only stay with the sign, which in this case is a negative value. So we know that before this first critical number, which is negative 1, the function is decreasing, right? It has a negative sign. Now, I will pick a value in between negative 1 and 0. For example, let's say negative 0.5. And I'm going to do the same thing. I'm going to find the value of the first derivative for a negative 0.5. So this would be 6 times negative 0.5 over negative 0.5 squared minus 1 squared. Okay? If we perform this, we would get a negative 3 over a positive value, which is 0.56. And this would give us a negative value again, negative 5.3. This is also a negative value. So as I told you, we only care about the sign. We don't care about the number. So we know that for this interval, the function is decreasing still. So something interesting is happening here, okay? Before doing the final analysis, I'm going to keep on selecting values. Here, for example, I can pick positive 0.5. So we're going to do the same thing, but now, Now we're going to evaluate for f prime of positive 0.5. So same thing, 6 times 0.5 divided by positive 0.5 squared minus 1 squared. Okay, if this was a negative value and the only sign that changes is this one, then this for sure must be a positive value, right? If you calculate this, you're going to get positive 5.3, and this is a positive value. So for this interval, we have positive sign. And finally, if we pick another value here, for example, 2, we're going to find f prime of 2. And we're going to get that f prime of 2. If you look at this, it's the same thing. The only thing that changes is a 2 here to a positive sign. So this would be positive 12 over 9. So this has a positive sign here. So we conclude that this is positive here. So what is happening here? You saw that in the previous exercise, every time we passed through a critical number, the signs changed, right? But in this case, it doesn't occur that. For this critical number, the sign is still negative in both sides. But then for this one, it changes. But then again, for this critical number, it doesn't change, right? So there's something happening here, and we're going to be analyzing that later on. But basically, it has to do with this. Because those two values were undefined, the signs didn't change, okay? But we're going to be analyzing that in future live sessions. For now, we only care about if the function is increasing or decreasing. So our conclusion would be the following. From negative infinity to negative 1, to negative 1, the function is decreasing because the sign is negative, right? Decreasing. We're looking at this, right? From a negative 1 to 0, the function again is decreasing, right? Decreasing. Then from 0 to positive 1, the function is increasing already, increasing. And finally, from 1 to infinity, positive infinity, the function is increasing again. Now, it is a mistake, since you see that, for example, from 0 to 1 and then 1 to infinity, it is a mistake to say that from 0 to infinity, the function is increasing. Why is that a mistake? Because for x equals positive 1, for x equals 1, the function is undefined, okay? So I cannot say that the function is increasing or decreasing for that specific value. That's why it's very important to separate those intervals, okay? So that's just one thing for you to consider. So this is the final result for this particular exercise. And now we're going to see one last one, part C. f of x equals x cubed. This should be much shorter than the one we just did. So part C, f of x equals x cubed. Let's see what's happening. Once again, remember, we need to identify the intervals for which the function is increasing or decreasing. So in order to do that, the first thing we do is find the first derivative. This is 3x squared. And then we set the first derivative to 0, right, in order to find the critical number or numbers. So this is 0 equals 3x squared. And here we're going to get that 0 is equal to x squared if we divide the 3. And the square root of 0 is still 0. So x equals 0 is our critical number. And there's only one critical number in this case. So this is a critical number. So we need to analyze what's happening here by doing our number line. So we do the number line here. We only have one critical number, which is at 0. So I'm going to see, once again, I'm going to study the sign of f prime of x. I'm going to duplicate this, bring it here. And we're going to pick a value right before 0, for example, -1, and a value right after 0, for example, 1. You can pick any value here. So if I evaluate f prime of -1, we're going to get, f prime is this function over here. So we're going to get 3 times -1 squared, and this is positive 3. So it has a positive sign. And if I do the same thing for 1, f prime of 1, we're going to get 3 times 1 squared, which is also positive 3. So something interesting is happening here again. So before 0 it's positive, after 0 is still positive. Okay, so something interesting is happening here. Although we calculate a critical number which does not produce an undefined answer such as what we got in part B, we still get the situation in which the function is increasing on both sides. And if we make a quick sketch of this graph, I'm going to make it here just for you to see. This graph would look something like this. And I'm doing this just because I know the function, but the idea is not to graph the function, but to analyze. But for you to understand what's happening, this is what the function looks like. Something like this. Let me do this again. Like that, okay? So what is happening here is what we know as an inflection point. You see that for this particular value, let me write this as inflection point. For that particular value, if I trace a tangent line, the tangent line would have slope 0, right? But although we get that value, we see that the function is increasing before that critical number, and after that critical number, it is still increasing, right? So that's what we call the inflection point, which we defined. I don't know if we defined that. No, we still haven't defined that. We're going to see that later on. But it's different from this case, for example, in which the critical number changed the trend of the function, right? In this case, in the one we're analyzing, it does not change the trend. It still keeps on increasing, but it's like it's an inflection point. That's the mathematical name for that. Okay, so that's the reason why we get positive and positive on both sides of the critical number. So to conclude this, we're going to say that from negative infinity to 0, the function is increasing. And from 0 to positive infinity, the function is still increasing. Okay, so with these 3 examples, we have seen all of the different particular situations that we can see when we're analyzing graphs, okay? And basically what we just saw, if we want to summarize today's class, is that the first derivative tells us if the function is either increasing or decreasing at a certain interval, right? And we applied that to 3 different examples, okay? In the next class, we're going to see how to calculate relative maximum or minimum points, and then we're going to be talking about the second derivative criteria, which talks about concavity of the function. Okay, so I hope this was clear for you, seniors. If not, please let me know, and we're going to clear it out in future live sessions. See you.